Hello, and welcome to a little video about Target 4CD, where we're going to look at exponential functions of growth and decay. The first thing that we're going to do in these notes is you're going to try to match the word problem to the equation and to the graph. Okay. My hint is to pay close attention to the numbers. All right. The first one. You put $1,000 into a savings account that earns 2% interest each year. Take a look at the functions, so the equations, and see which one do you think will go to the putting $1,000 into a savings account. Hopefully you chose the letter E because you saw the 1,000 there. Now look at the 6 graphs. Which one do you think matches our graph? Use the same kind of idea as you did to match the problem to the equation. Do you see how the 6th graph has 0, 1,000? Because that's our starting point. So, equation E, graph 6. A person takes 800 milligrams of ibuprofen to treat a migraine. Each hour, the amount of ibuprofen in a person's system decreases by 25%. Pay close attention to the numbers and match the equation. Hopefully you picked equation F because of the 800 milligrams of ibuprofen. Take a look at the graphs. Which one do you think matches the problem? Use the same kind of deduction. Graph number 2 has that 800. I forgot to mention in letter E, or I guess in the first one, we were putting money into an account. The graph for 6 is going up, it's increasing. For this one, the amount of ibuprofen decreases. So our graph is decreasing. And it's graph 2. Okay. There are about 11.7 billion Alaska skull crabs in 2018, but their population decreased at a rate of 35% each year due to warming ocean temperatures and overfishing. Find the equation that matches. Hopefully, you chose equation B because of that 11.7. Remember, in this problem, it's decreasing. So find a graph with a similar number and a decreasing domain. Or I guess range, decreasing range. If you take a look, the first graph has 11.7 on it. So graph 1. The next problem, there are 2,379 confirmed COVID-19 cases at the beginning of March 2020, and the estimated exponential growth of new cases is 13% per year. If you want a chance to pick out the equations yourself, I'm going to tell you which ones they are for these 3. So if you wanted to take a moment, you can pause after you can read each of these problems and figure it out yourself. Okay. I would pick letter A here because of the 2,379, and using that same logic, I would pick the 3rd graph. The next one, a population of 27 cells of E. coli will double every 15 minutes, meaning the population will increase about 1,500% every hour. This matches with equation C. And the graph is that's supposed to be graph 4. Lastly, we got the 80,000 terabecquerels. I don't think I'm saying that right, but it's a big amount of a radioactive isotope, which was released in the 1986 explosion in Chernobyl when the nuclear reactor exploded. The half-life of this radioactive isotope is about 30.19 years, meaning it decays in the environment at a rate of 2.3% a year. So I'm looking for that 80,000. That's in letter D. And again, looking at my graphs, there's my 80,000 in the 5th graph. What we looked at here are exponential growth and decay equations. Exponential growth and decay, their equations are very similar. There's only one difference. And let's write down the equations and then define some of the variables. For exponential growth, we would have f of x equals a 1 plus r to the power of x. Exponential decay, on the other hand, is a1 minus r to the power of x. So growth has a plus, decay has a minus. Now what do these letters mean? In our function, a is going to represent the starting amount, and r is going to be our percent rate in decimal. That is not how you spell decimal. Wow, Gooman. There's a C in there. There you go. So, that's all we really need to know is the starting amount and the rate as a decimal. Now, when we're identifying exponential growth or decay equations, in word problems we look for words that that model something that's growing, so increasing, earning. Decay would be something like decreasing, losing, things like that, or depreciating. So those kind of words. Now, if we're just looking at the function itself, the easy way to tell, of course, is the plus and minus. However, sometimes there's no plus and minus within the parentheses. So what we think about is the number in front of the parentheses, inside the parentheses, bigger than 1 or smaller than 1? If it's bigger than 1, it's growth. If it's smaller than 1, it's decay. With all that in mind, let's take a look at this problem and identify the functions as growth or decay. It's all about those parentheses. In this parenthesis for letter A, we have a plus, so that's growth. Letter B, we have a minus, it's a decay. In letter C, we have a decimal, and this decimal starts with a 0, so it's smaller than 1. In letter D, we also have a decimal. However, this decimal starts with a 1, so that's growth. In letter E, we have a minus, that's decay. And in letter F, we have 5/3. 5/3 is the same as 1.66666 repeating forever and ever until the end of time. That's bigger than 1, so it's growth. What we're going to do in number 3 is just write the exponential function that models these situations. All right, so letter A, we have a $25,000 home that increases 6% annually. Actually, I want to use purple for that. Okay, so f of x equals our starting amount, 1 plus, because we're increasing, I lost a 0, and 6% as a decimal is 0.06. The way we find out a percent as a decimal is we do the number that is our percent divided by 100, and that gives us our decimal, power of x, 250,000, increasing by 6%. Next, we have a $5,000 refrigerator that decreases in value by 3.2% annually. Annually means once a year. I forgot to mention that in the previous problem. So we start with 5,000. We have a 1 minus because it's decreasing. And our rate as decimal is 0.032 to the power of x. Decreases 3.2. Okay, we bought a new car for $25,000 that decreases in value 15% each year. Now, unfortunately, the first year that you get a car, it decreases about 20%, and then after that, it decreases 15% a year, which kind of sucks, but that's the way the market is. Anyways, we get a function that is 25,000, parentheses, 1 minus, because it's decreasing, 0.15, because that's 15% as a decimal. A baseball card you bought for $5,000 increases, okay, in value 5% each year. Let's write our function. F of x equals 5,000 times 1 plus, because we're increasing, 0.05, because that's our percent in decimal form. We got a population of ants that starts at 30 and increases by 50% each year. So we got f of x equals 30, 1 plus, because it's increasing, 0.5, because that's 50% as a decimal. All right, last one here. Your heart rate reaches 140 beats per minute and then decreases by 10% each minute. F of x equals 140. 1 minus, because we're decreasing, 0.1, because that is 10% as a decimal. Okay. Next, let's actually apply this. Let's do some problems, let's graph them, and use our calculators a bit. In number 4, we have a population of ants that starts at 50. So this had a bigger starting population. And increases at about a rate of 15% each month. Now, the first thing that we need to do is write a function to represent this problem. Let's go f of x equals 50, because that's how many ants we started with. Parentheses 1 plus, because we're increasing. And then 0.15, because that's 15% as a decimal. Of course, to the power of x. All right, what is the population after 5 months? Well, to find that out, we're going to plug in 5 into x. You're really just going to put this part into your calculator. What we get is 100.56, but we can't have 0.56 of an ant, so I'm just going to round it down to 100. Next, we have, what's the population after 10 months? Well, we're going to do the same thing. We're going to take 10, and we're going to plug it in. Oh, I cannot resist color coding. I must. Okay. We're going to plug it in that same equation, but with a 10 in the exponent. Just this part goes into our calculator, and we get about 202.277 ants. We can't have 0.27 of an ant, so I'm going to round down to the nearest whole, 202. Now, how would we graph it? Well, we start with the y-intercept. The y-intercept always represents our starting point. Keyword start. So we have a y-intercept at 0.50. I don't know why I wrote it down there. I'm going to put it back up here. There we go. Oh, the parentheses didn't come with. Oh well. Let's try that again. Just going to draw them. Bloop, bloop. Okay. Let's put a dot at 0.50. Next, we already solved the 2 more points. We solved for the point 5, 100, because we plugged in 5 for x, got 100 for our y, and we also got 10, 202. Let's graph it. 5, 100, 10, 202. Here's our graph. Next, a Tesla Model S, which has an MSRP of $95,000. That means that's how much it costs brand new at the current market rate value, decreases in value about 16% a year. Again, just like every car, it is going to decrease 20% that first year and then 15% each year after that. I think 16% is also a good estimate because electric cars are kind of new and not very affordable for everyone. So we decided 16% is a better percent to look at this than 20. Anyways, let's write a model for this situation. Got f of x equals $95,000 because that's where it starts. And it decreases in value, so I'm going to be subtracting. And I'm going to put 16 as a decimal 0.16 to the power of x. Now remember, we already got our y-intercept here, 0.95,000, because that's the starting point. Perfect. Let's find the value after 5 years. Just like before, we're going to plug 5 into this function. Again, keep in mind this is actually going to be a little bit less. Actually, in real life, it's going to be less than this because of that first year and that value loss. But we're going to go ahead and plug 5 into x. And just this part goes into our calculator. No, that was green. I wanted blue. Blue. When I plug this into my calculator, I get, now you ready for this? The value of a Tesla after 5 years. It's going to be $39,730.13. Yeah. So we got this point to graph. Of course, we're going to estimate with the decimal point. Let's find another point by plugging in 10. So after 5 years, it's $39,000. Imagine how much it's going to be worth after 10 years. Or maybe you're guessing in your head, I don't know. But let's plug it into our calculator and find out how much it's really going to cost after 10 years. You ready? You ready? It's going to cost $16,615.62. And that's if you took really good care of it, right? If you didn't take great care of it, it might be worth less money. All right, we got 3 points to graph. Let's do it. 0, 95,000. 5, 39,000. I guess it's like right here. Then we have 10, 16,000. Look at how quickly that value goes down. Sucks, right? That's the car market for us. Number 6, you are considering depositing, which means putting in. Ooh, okay, that's growth, increasing. $500 into an account that pays us 1.5% interest. You might be thinking, wow, that's not a lot. You'd be right. Banks do not offer you that much interest for holding your money, but it's something. So first let's write a function. F of x equals 500, 1 plus 0.015 to the power of x. And again, on the note of, the very little money that you're going to be earning if you use a savings account, if you don't put your money into a savings account, it doesn't grow at all. So, yeah. Let's see how much money we're going to have after 15 years. And this is us assuming we have not touched the money, not at all. Oh, right, we have our 0.0500. So first we're going to put in 15 into our function. Again, that means we haven't put in any extra money. Now, if I were you and I had a savings account, because this is something I do, I would continue to put more money in there, right? Because the more money you have, the bigger the interest you'll get, which is, still not a lot, but like I said, is something. Okay, after 15 years, we will have $625.12. Well, let's see how much we'll have after 50 years. Again, this is untouched. It means you haven't put in any money, you haven't taken any out. When we put in 50 into our calculators, into this function, we end up with $1,052.62. So it barely doubled after 50 years. So you're not really earning that much interest. Okay, so 0, 500, 15, 625. Whoops, didn't mean to draw that. Or that. I was supposed to do the eraser. There we go. All right, 15 and what is 625? So that's, I don't know, right there. And then 50 and 1052, probably right here. There we go. Very slow growth. Number 7. You take 1,000 milligrams of Tylenol. Every hour, the amount of Tylenol in your body decreases by 24%. Alright, we have a decay function here because we're decreasing. And this is very important information. This is how dosages are figured out, right? This is how doctors know how much to prescribe you and how often to give you. Alright, let's write our function. 1,000, 1 minus, because decreasing, and 0.24. And of course we do have our starting point. Decreasing. Whoops, wrong color. Alright, let's see how much Tylenol will be in our system after 4 hours. So let's plug 4 into our function. Remember, just this part's going in. After 4 hours, we have only 333.62 milligrams. So that's a third of the amount. I think, and I'm going off the top of my head right now because I don't have a bottle of Tylenol in front of me, but I think you are allowed to take it every 6 hours or so? 6 to 8? 4 to 6? I'm not sure. Something like that. Because after 4 hours, there's a third. So maybe 6 to 8? Anyways, let's see how much Tylenol is left in our body after 12 hours. Alright, I'm gonna guess very, very little. Very, very little. Yeah, we have about 37 milligrams in our body after 12 hours. Alright. Let's graph this. We start off with, oh, it's not 100, it's 1,000, 0, 1,000. Then we got 4 and 333 here. And then we have 12 and 37. So it gets out of your body, whoops, pretty quickly. All right. Number 8. A construction company bought a new bulldozer for $120,000. Unfortunately, the value of the bulldozer depreciates, goes down, exponentially at a rate of 20% per year. Let's write a function to represent this bulldozer over time. Got f of x equals 120,000, 1 minus 0.2 to the power of x. Let's fill in the table and the graph. Now, what I'm going to do is what we did in all of these problems and plug in 0, then 1, then 5, then 10, then 12, and 25 into our function. Alright? And to save time on this video, I'm just going to fill this out. If you're doing this on your own and following along, absolutely pause this video and fill this out on your own. Ready? Alright. When I plug in 0, I have 120,000. So that's the starting amount. After 1 year, it's worth 96,000. After in 5 years, it's 39,321.6. After 10 years, it's only worth $12,884.9. Oh, I guess 90 cents, 60 cents. After 12 years, its worth is 8,246.34. I'm going to try that 8 again. It came out ugly. And of course, after 25 years, it's barely worth anything. $453.35. Let's graph. All right. 0, 120,000. So that's right here. After 1 year, it's 96,000. It's kind of a guess here, right? Because if that's 100,000, that's 90, and 96 is somewhere there. After 5 years, it's 39,000. So 10, 20, 30. Well, I think this got moved when I printed it. I'm going to recount these. All right. 5, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. Okay, better. 120. So if that's 100,000, then 96,000 is there. If this is 50,000, then 39,000 is like right there. And let's find 10. It's 12,000, so it's a little over this. 12 is 8,000, a little under the 10,000. And don't have 25 on the graph. Okay. The company wants to sell the bulldozer and make at least 30,000 in the sale. Use the graph to estimate when that should happen. All right. So this says 30,000 right here. So let's see where that hits the graph. Oh, right here. So I would sell it after 5 years. Or at 5 years-ish. Yeah. Sell it. I wouldn't. So part of me is tempted to say between 5 and 6, but like, it's less than 30 soon after that. I would say sell it by the 5th year. Yeah, that would be safe. That would be safe. Okay. Letter D, approximate the nearest year which the bulldozer will have this worth. Okay, 50,000. Oh, that's 50. All right, here's 50. So it'll be about after 3 years. And then 10,000. So that's 10,000 right here. About after 9 years. When will the bulldozer be worth 0? Oh. I don't think it could ever be worth $0. Never. It's always going to be worth something. First of all, we talked about asymptotes, remember? In this function, there's absolutely nothing that you could plug into x that'll get 0 as an answer. That's just algebraically. When we apply it to real life, it's never going to be worth $0. It will always be worth something. So never. Algebraically, because of the y equals 0 asymptote, and IRL, it will always, maybe not always, but for quite some time, be worth something. So I'm sure they could sell it even for $100. Maybe they can't sell the whole bulldozer. They can sell its parts, right? Because some people will have that same bulldozer and want to fix it instead of buying a new one. Maybe you can buy a new one, but sell the parts of this bulldozer. So it's never going to be worth nothing. Okay? You can always sell something from that bulldozer. The worth will not just be zero. Okay? So algebraically, it's because of the asymptote, but when we think about it in real life as well, it's never just going to be worth nothing. It's a big thing of metal. At the very least, you could sell it for the metal. Okay, that's our unit. I hope you could see how exponential functions are so practical and so prevalent in real life. I can't wait to do a little project with you about this, but for the time being, have a wonderful rest of your day. Bye!